the most important thing in both Gauss's law and Ampere's law, as I have discussed, to find the suitable Gaussian surface in case of Gauss law and suitable curve or path in case of Ampere's law, and use method of symmetry so that integration part, flux part in Gauss's law and circulation part in Ampere's law, that is dot product part, in both cases can be found easily without actually using integration. That is the expression where we use integration, but when we use Gauss's law and Ampere's law to simplify the problems, there we choose this Gaussian surface and curves in Ampere's law so that we can easily found integral part, flux part or line integral part. That extensively simplifies the problem to find electric field by Gauss's law and magnetic field by Ampere's law. First of all, an infinite linear charge in a line, just that there is a wire. So charge density per unit length is equal to Q by L. Let the unit length charge in this infinitely long wire is sigma. That is the charge density per unit length. So here we will create a Gaussian surface to find electric field. So we have to create Gaussian surface in such a way so that we can easily find this surface integral throughout this Gaussian surface. As we are finding dot product, so we have to create surface so that this dot product can be found without actually using integration. So let at distance r, this is distance r, and this is distance at point P. We want to find electric field, and this is the uniformly plus charge, positively charged wire having linear charge density Q by L or sigma. So we will create a Gaussian surface, imaginary Gaussian surface, that is a cylindrical surface, and you will see how the cylindrical surface simplify the problem, and Gauss's law can easily be used in this cylindrical surface. So this is a cylindrical surface, this is cylinder having axis coinciding with the wire, positively charged wire. So we have to find dot product of electric flux, electric field throughout this closed cylindrical surface. So now we know this is positively charged, so this is the curved area of surface. So all these points on curved area are at same distance from the wire. So these points are symmetric. Hence the magnitude of electric field will be same by symmetry at all points on this surface. Because these points are symmetric, so they will possess same value of electric field by the virtue of symmetry. And electric field direction, we know this is positively charged, so this will be away from the wire. So at all points electric field is away from the wire. In this curved region, electric field is away from the wire, and all points on this curved surface of cylinder are symmetric with respect to this axis. This is the axis of cylinder which coincides with the wire, uniformly charged wire. So these points will have same amount of electric field by symmetry. Now consider small areas dA. So the vector dA will be outward from the closed surface. So this is vector dA, hence vector dA and E are in same direction. So throughout this closed cylindrical surface, all small dA elements will be parallel to electric field. This is toward this side, here dA vector will be toward this side. So we want to simplify this dot product. So we can see here, for all small everywhere in the curved region, E is same. Value of electric field by symmetry. We have used the method of symmetry. At all points, amount of electric field is same because they are symmetric relative to the axis, which is also the position of charged wire. So the electric field will be same and radially outward. We know by Coulomb's law it will be radially outward. E dot dA will be simple mod of E into mod of dA. So for all small parts, you will carry out E dot dA in this curved surface. So you will find it is E into the area of curved surface is 2 pi r. That this is the length of this cylinder is L. 2 pi r L. So the dot product along the curved area is E into 2 pi r L. Similarly, this flat surface, two flat surface, circular flat surface. Here also, you see dA is perpendicular, that is outward from the surface. This is the direction of dA, and direction of E at all these points will be outward from the wire. So in these flat surfaces, this is direction of dA and this is direction of E. So E and dA are perpendicular. So in this flat surface, E dot dA will be 0 at all points. Similarly, at this flat surface, E dot dA will be 0 at all points. So dot product of this and this surface is 0 plus 0. So total dot product, that is total flux E dot dA through the closed surface is 2 pi r L E. Now, by Gauss's law, this is equal to Q net by epsilon 0. Q net is charge inside this closed surface. So this is the length L and linear density is sigma. So charge in this part of wire is sigma into L. That is the charge Q net. So you can say flux is equal to net charge, that is QL by epsilon 0. You can cut L. So electric field you can easily find. Electric field is equal to sigma by epsilon 0 2 pi r 2 sigma pi r. So this is the electric field at distance r from wire, which has been easily found by Gauss's law. We have used method of symmetry and properly imagined a Gaussian surface, that is cylindrical surface, so that the dot product throughout the closed surface can easily be found without carrying out integration. You can put sigma is, let this wire is length is L, let the total length of wire is L, then sigma will be Q by L. So you can find E is equal to Q by 2 epsilon 0 pi r L. If the length of wire is L and charge on total wire is Q, then electric field will be this Q by 2 epsilon pi r L. And please remember, this is only true when R is very less than L, because we have assumed the condition that wire was infinitely long. Hence, all these points were symmetric for the wire with respect to wire. When this wire has finite length, then these points will not be symmetric, because at this point, wire, the charge faced by this point will be less, charge faced by this point will be more. So they may have different electric field. whereas we have assumed uniform electric field throughout this curved length because the wire was of infinite length. So this infinite length concept which we have used to find the uniform electric field, it will only be true in this case when we use Q instead of sigma, when we use Q and finite length L. That is only true when L is very, very larger than R. So if the point P is very close to this wire, then the length and the length of wire is appreciably greater than R, then we can assume the wire is infinitely long. This is only for infinite length and this is for finite length, but this can only be used when R is fairly larger, when L is fairly larger than R, that is the length of wire is appreciably greater than distance of point from wire where we are finding electric field. So both these formulas, this is more correct because here we have used infinitely long wire and this is for finite length. So here you can see how easily we can find electric field with the help of Gauss's law. Only we have to cleverly choose the Gaussian surface so that the dot product for whole surface can easily be found. Here we have not used integration, just by logically we have found here it is perpendicular, so for these surfaces dot product is 0, and for curved surface E and dA are parallel, so their dot product is just multiplication of modulus of E and modulus of area. So that is area is 2 pi RL, curved area, and E is uniform throughout the curved surface. So that way you can easily find electric field by using Gauss's law. Again we will use Gauss's law to find electric field. This is uniformly distributed sheet. Charge is uniformly distributed and this sheet is the physical thickness of sheet is very low. Only charge plus Q charge is distributed in a sheet which has almost zero thickness. Sheet thickness is negligible and the sheet has charge density, that is surface density, is Q by A sigma. Here it is Q by A, surface charge density sigma. Now we have to find charge at point P. Charge at point P, which is located, and this is infinitely long sheet. This is located at distance R. So we have to create a Gaussian surface wisely so that this dot product can easily be found. Here we can see that Gaussian surface is horizontal cylinder. Unlike linear charge distribution which we have earlier solved, problem of linear charge distribution, here the Gaussian surface you can choose is horizontal cylinder. There we have selected a vertical cylinder. Here horizontal cylinder surface, Gaussian surface will give you easy calculation for flux. Radius of this curve is small r. Flat circular face is small r. So this is the point P. So now we have to find total flux through this horizontal cylindrical surface. So by symmetry, again we will use method of symmetry. This is positively charged, so near this surface electric field will be away from this charge sheet. Right side it will toward rightward and left side it will be leftward, electric field. And as these both faces, circular face, are at same distance, so all these points on this circular face are symmetric. They are at equal distance from this sheet. So by symmetry, they will possess same physical property. Hence the electric field at all points in this circular flat surface will be same, and its direction is towards this side, rightward side. And dA, area vector, small area vectors in this flat surface will be outward from this surface. Same argument here, it will be E at all points, and for all dA vectors, small dA vectors, direction will be outward from the surface. So dA and E are in same direction, and dA and E is in same direction. Now for this curved path, this path, you can see area vector is perpendicular to curved surface, whereas vector E will have away from the sheet direction. This is vector E. For whole curved path, dA and E are perpendicular. So dot product for whole curved path will be 0. So that we have simplified. For curved path, we have found dot product just by seeing the direction. They are perpendicular. Electric field and area vectors, all small area vectors in this curved path will be perpendicular to electric field. Hence dot product throughout this curved surface will be 0. Now we have to find dot product only for this flat surface and this flat surface. For this flat surface, for a small area, dot product is E dot dA. E is uniform by symmetry. E is same at all points in this. So it is mod of E into mod of dA, because both vectors are in same direction. So that will be just multiplication of their magnitude. Now E is same at all points. So when you will calculate for different area elements, you will find total area. Then total area is pi r square. So dot product for this face is E into pi r square. Similarly for this face, it will be E into pi r square. So for total surface, curved surface, it is 0. So total flux 0 plus E into pi r square plus E into pi r square. So total flux is 2 E pi r square. Easily we have found total flux without integration. That is the trick to select the Gaussian surface, so that total flux through the Gaussian surface can be found easily. You should not use actual integration. Q net by epsilon. Q net is charge enclosed by the cylinder. So when it will cross this sheet, this will cut the sheet in circular flat area equal to this flat surface, that is pi r square. So area of the sheet is pi r square into surface density is sigma. Surface density is sigma. So total charge inside this horizontal cylinder is area of this sheet cut by the horizontal cylinder into surface density of charge. Area is pi r square is the radius of this horizontal cylinder. So this pi r square you can cut, and this divided by epsilon 0 by Gauss's law. So E is equal to sigma by 2 epsilon 0. This is electric field. Here sigma is charge density of this flat charge sheet of infinitely thin thickness. So this is the electric field. If you use this formula for sheet of finite dimensions, then put sigma is equal, this is the standard formula for infinitely long sheet. That sheet has finite area A, then put sigma is equal to Q by A. Q by A epsilon 0 2 into epsilon. So this is electric field for finite sheet, but this electric field is only valid, expression is only valid when point P is very close to this sheet. Hence, if the length and width of sheet is given, so this distance of point P should be very less. It should be very close to sheet. Only then this formula you can use, because this formula is called infinitely long sheet. Sheet having infinite area, and this formula is for area sheet. You can use this formula like this: a sheet having charge Q and area A only when electric field you are calculating for a point which is very close to sheet. Only then this sheet will act as infinitely large sheet for that point, when this point is very close to the sheet. So this was Gauss's law to find electric field near a infinitely large charged sheet. Now we will use Gauss's law for real sheet. So this is a real sheet. This is a real sheet, and we have injected a charge Q plus Q. So we know inside the conductor charge electric field will be 0, hence the charge will distribute at the outer surface only. So let this phase has plus Q1 charge. So this will have Q minus Q1 charge. Both phases will have same charge, that we will prove later. But presently assume that this is out of this plus Q charge, plus Q1 distributes on this phase, and the remaining charge Q minus Q1 distributed on this phase. Now this is also positive. Now we know inside the conductor electric field is 0. So now put the formula of infinitely long sheet. If the thickness is very small, then we can assume these sheets as infinitely long sheet. So infinitely long sheet, electric field is sigma by 2 epsilon 0, or Q 2A epsilon 0 for finite dimension sheet. But the sheet thickness we have assumed very low, hence a point inside this sheet will be very close to flat surfaces. Hence we can assume these surfaces as infinitely long surface for this point P. So electric field due to this surface is electrical charge surface, which we have discussed earlier by Gauss's law. We have found for an electrically charged surface, electric field is given by this formula. So this surface will exert electric field in this direction, and this surface will exert electric field in this direction. So this is right surface, this is left surface. So electric field due to right surface will be Q by 2A epsilon 0, Q minus Q1. Charge on this surface is Q minus Q1. Similarly, by left surface, electric field is Q1 by 2A epsilon 0, A. Because inside the conductor we have discussed electric field is 0, hence ER and EL, which are in opposite direction, they will be equal in amount and opposite to each other. So you can say ER is equal to EL, and this says that Q minus Q1 is equal to Q1. Equated these, and this says that Q1 is equal to Q by 2. That means Q1 is Q by 2, and Q minus Q1, which is Q by 2, and this will also be equal to Q by 2. So you can say when you inject a positive charge in a sheet, this charge equally distributes on both faces, q by 2 on this face and q by 2 on this face. So this formula of a charged sheet you can use for real sheets also in a suitable assumption. Here we have assumed for a sheet is very thin, hence the point P, for point P, both these surfaces act as infinitely large surface, infinitely large charged surfaces. And for a single surface, charged surface, electric field is given by this formula. So this formula you can use many places to simplify the problem. So another conclusion we have drawn that when a charge is given to a conductor, a sheet, that this charge is uniformly distributed at both faces of the sheet. Another example which we will understand with the help of Gauss's law, that there is a constant electric field E existing. Electric field E is existing and a metallic plate is placed in this electric field. This is very large metallic plate, so we can use the formula of infinitely large charge surface. So this metallic plate is kept. Let the area of every surface is A. Now we have to find what charge will appear on both these surfaces due to this external electric field. So as we know, this is placed in the electric field, so these surfaces will have induced charge. So by logic you can find at this surface the induced charge will oppose this external electric field. So induced charge will be in opposite direction, that is in this direction. Induced electric field, E dash, inside the plate. So this surface will have positive charge, positive induced charge, and equally same magnitude negative charge will appear on this surface. That you can find by logic, because induced charge will oppose the external electric field. Now what is the magnitude of this induced charge that we have to find? So just imagine a point P inside this plate, and this is face 1 and this is surface 2. Now at this surface net electric field is 0. EP is equal to 0, we know, because point P is inside the conductor. So we have discussed inside the conductor electric field will always be 0. Now we have to find different fields, that is first electric field is this, at this point total electric field is, first is electric field, let rightward direction is positive and leftward direction is negative. This external field will create at point P an electric field of magnitude E in right direction, which is positive direction, plus surface 2 of this plate will create electric field in reverse direction, that is left direction, and this will be sigma by 2 epsilon 0. As it is in reverse direction, hence it is minus. Similarly, surface 1 will also create electric field at point P in same reverse direction, so this will also be negative, sigma by 2 epsilon 0, and the total electric field is EP is equal to 0 because point is inside the conductor. So we can say sigma is equal to epsilon 0 into E. Sigma is epsilon 0 into E. So both these surfaces will have charge density epsilon 0 into E. Charge density at this surface, positive charge at this surface also, epsilon 0 E charge density will exist due to induction of charge. If the area of this surface is A and area is fairly large relative to distance of point from both these area, then we can say charge density is equal to Q by A. Hence this formula of infinitely large charged surface can be used, and this can be written as Q by A is equal to epsilon 0 into E, because sigma is equal to epsilon 0 E. So you can say induced charge is equal to epsilon 0 E A. So this surface will have plus epsilon 0 E A induced charge, and this surface will have minus epsilon 0 E A induced charge. A we have put here because we have assumed that the surface area is very large compared to distance of point from both surfaces. Hence the formula for infinitely large surface having charge distribution sigma, charge distribution density sigma, can be used here. So at both surfaces minus epsilon 0 EA plus epsilon 0 EA charge will induce due to this electric field E, where A is the surface area of plate and it is fairly large compared to distance of point P from both surfaces. Now we will discuss another case. This sheet we have given a charge plus Q. So from earlier discussion we can say this face will have plus Q by 2 and this face will have plus Q by 2, and this sheet is neutral. Here we have given external plus Q charge and this sheet is neutral. So what will happen with this sheet? So let this surface of sheet assumes minus Q dash charge, because this is positive, so induced charge at this surface will be negative. As this sheet is neutral, so this surface will have plus Q charge. Total charge on this sheet is 0. So by Gauss's law we will find what will be the value of this charge. So just create a Gaussian surface inside the conductor. We are creating Gaussian surface inside the conductor because inside the conductor electric field is 0, we know. So we will easily find E dot dA. Let these both sheets are very close to each other, so we will omit this length. So this Gaussian surface E is 0 here and E will be 0 inside this conductor also. So total dot product will be 0 for this Gaussian surface, and this is equal to charge enclosed by this surface. Charge is plus Q by 2 minus Q dash this surface charge and plus Q by 2 this surface charge. Divided by epsilon 0. Gauss's law, Q net by epsilon 0. So Q net inside this surface is this surface charge, that is minus Q dash, and this surface charge, that is plus Q by 2. Plus Q by 2 minus Q dash, that is net charge divided by epsilon 0. So here you can say Q dash is equal to plus Q by 2. So induced charge on this surface will be plus Q by 2. Hence, Q dash will be Q by 2. It is not plus because we have already assumed it is minus. So this is minus Q by 2, and as the whole charge is constant, so this surface will have plus Q by 2. This we have already discussed that facing surfaces will always have same and equal charge, whether they are flat surface or they are circular surface, whatever their shape is. We have discussed in ice pail experiment that facing surfaces will always have equal and opposite charges. So if this is plus Q charge, then this will be minus Q charge. Here also we have proved by Gauss's law by creating this Gaussian surface, and this length we have assumed very low, and we have assumed that these plates are very close to each other. So dot product at this part is not necessary, and electric field inside this conductor is 0. So for this portion dot product is 0, and this is very small, so we have omitted it. So for flat facing surfaces, charge is always equal and opposite. So this have been injected plus q charge, this will distribute plus q by 2 here, plus q by 2 here, and this will induce minus q by 2 on this facing surface, and this surface will get plus q by 2 charge. So these are very important conclusions which you can draw based on Gauss's law and by the rule that inside the conductor total charge is 0. Again we will use same method. Let this is uniformly thin sheet. It has plus q charge, it has minus q charge. So electric field at this point, this is sheet number 1, this is sheet number 2. By sheet number 1, this is plus, so electric field will be in right side, that right direction is positive and left direction is negative. So E1 is equal to plus q by 2a epsilon 0. Similarly by 2, it is negatively charged sheet, hence electric field by this sheet will also be in this direction. So E2 is equal to plus q by 2a epsilon 0. Total field inside this plate is E1 plus E is equal to addition of both these will be q by a epsilon. So this is the total field inside these two sheets which have been assumed infinitely long, or we can say when you are using A, that means these are finite sheets, then you can say that their distance is very less, hence the point is very close to both these sheets, and hence for this point these sheets can be assumed infinitely long. In our case of capacitors, we use same discussion, same arguments to find the charge on plates of capacitors, to find electric field, etc. Similarly, for this point, electric field by this sheet is in this direction, that is q by 2a epsilon 0, and electric field by this plate will be in this direction, that is in this direction, q by 2a epsilon 0. We are assuming that this point is also very close to these sheets and their dimension is very large compared to the distance of this point from the sheets. So both these fields are in opposite direction, hence net field in this area is 0. Similarly in this area, E1 this is positively charged in this direction, it is q by 2a epsilon 0, and E2 this is negatively charged, so field will be in this direction, E2 is q by 2a epsilon 0. So E1 and E2 are equal and opposite, so in this region also field will be 0. So for these two plates plus q and minus q charge, field in this region will be 0, and field in between these plates will be twice of field created individually by every plate. So these are different cases. You can yourself make other cases also, how the charge will distribute, how the field will be there, etc. etc. Now we will discuss another example. Let these are three plates of equal area A, and all these distances are very small, so we can use the formula of infinitely large area. We know electric field by infinitely large area is sigma by 2 epsilon 0, or it can be written as q by 2a epsilon 0. For A having very higher value, corresponding to distance of any point P where electric field is being found. So this is the problem. This middle plate has external charge plus Q, and these end plates have been connected with a battery, and this battery supplies a plus Q small q charge and minus small q charge to both these end plates. Now you have to find at every surface what will be the charge distribution. What will be the charge distribution in equilibrium? So let plus Q charge is applied to this. Let out of this plus Q, Q dash charge goes at this surface. So this surface will have Q minus Q dash charge. As this surface has Q dash charge plus Q dash charge, so this facing surface will have minus Q dash charge, which we have discussed due to Gauss's law. When you will assume a imaginary surface going through inside this plate and inside this plate and apply the Gauss's law, then both these charges will be equal and opposite on the facing surfaces. And this is minus Q charge, and total charge on this plate is plus Q. Hence this, by charge conservation, this part of the plate will have Q plus Q charge. This is plus Q charge, small q charge will appear at this surface. So this and this are facing surfaces, so this surface will have minus Q plus Q charge. Facing surface will always have equal and opposite charge by Gauss's law. As the total charge on this plate is minus Q, hence this surface will have Q plus small q, this is Q dash, so this will be Q dash, this will be Q dash, this will be Q dash, and minus Q. At this phase, the charge will be minus Q. So this is the equilibrium charge which we have assumed. Now we have to find the value of Q dash, because Q, capital Q and small q are known. So we have to find the value of Q dash to find the equilibrium charge at every phase. So let this is phase 1, this is phase 2, this is phase 3, this is phase 4, this is phase 5, and this is phase 6. So every phase can be treated as a charged sheet of infinite dimension, because we have assumed that these distances are very small. This distance are very small. So the charge at any point in this area can be found by the formula of infinitely large charge sheet. Infinitely large charge sheet formula, we know this, Q by 2A epsilon 0. When area is very large and point P where charge is being found is very close to the surface, then we can use this formula of infinitely large surface charged sheet. Now just assume a point P inside this plate first. Where anywhere you can assume this point P, inside this or inside this, that doesn't matter. Now at this point is inside the conductor, hence net electric field inside this plate will be 0. Inside field, electric field inside a conductor is always 0, that we know. So now what will we do? We will find at this point electric field due to every individual surface, 1, 2, 3, 4, 5, 6. Every surface will create its own electric field at point P, and the resultant electric field at point P will be net resultant of all electric field created by every surface, and that will be 0 because this point is inside the conductor. E1, we will call E1 electric field due to surface 1, E2 electric field due to surface 2, E3 at this point due to this surface, E4 due to this surface at this point, E5 due to this surface at this point, and E6 due to this surface at this point. And rightward electric field we will assume positive, and leftward electric field we will assume negative. So at this surface, so EP is E1 plus E2 plus E3 plus E4 plus E5 plus E6. That is EP. At this point, electric field is due to resultant of electric field due to all these surfaces. So EP is equal to 0 is equal to, due to this surface electric field, this is positive charge, so electric field will be in rightward direction, so it is positive. So plus Q minus Q dash by 2A epsilon 0. This is E1, electric field at P due to this surface. Now with this surface E2, due to this surface, this is positive surface, this will exert electric field in left direction, so it will be negative. So this is minus Q dash by 2A epsilon 0. This is E2, E1, E2. Now E3, this is negative, so electric field will be in rightward direction, so this is positive. Electric field is positive. Q dash by 2A epsilon. This is E3. Now electric field at point P due to surface 4. This surface is positively charged. Q plus Q dash. So this will have electric field in left direction. So that is negative electric field. Q plus Q dash by 2A epsilon 0. That is A4. Now A5. E5. This is negative charge, Q plus Q dash. So it will be in rightward direction. Electric field will be in rightward direction at point P due to charge surface 5. So this is plus Q plus Q dash by 2A epsilon 0. Similarly, this surface, this is minus charge, hence this charge is positive. This is negative charge, so total charge this is positive. So this will create an electric field in left direction. So this is minus Q plus Q dash minus Q by 2A epsilon 0. This is E6. This is E6. E1, E2, E3, E4, E5, E6 at point P. These are individual electric field created by each surfaces at point P. Now this can be cancelled. This can also be cancelled. So we have this is this plus this is equal to 0. So we can say Q minus Q dash minus Q dash plus Q by 2A epsilon 0 is equal to 0. We have added this part and this part, and this addition is 0. 2A epsilon 0, Q minus Q dash minus Q dash plus Q dash, plus Q. So this can be written as 2Q minus 2Q dash. 2Q minus 2Q dash is equal to capital Q. So we can write Q dash. We can write Q dash here is equal to 2Q minus Q divided by 2. 2Q minus 2Q dash is equal to Q. So Q dash is 2Q minus Q divided by 2. From this expression you can write Q dash as 2Q minus Q by 2. So we have found Q dash, this charge. Now we can find charge at every surface in terms of Q and capital Q. So just put the value of Q dash at this surface, at this surface, at this surface. So you will find charge at every surface. So this is how you can find distribution of charge with the help of Gauss's law. So this is another problem. This is also very simple problem. It was asked in IIT 2009. So this problem was asked in IIT 2009. This is very simple problem and based on Gauss's law. So what is given? These are three spheres. 1, 2, 3. Three spherical shells of conducting material. 1, 2, 3. Inner sphere has radius r. Outer middle sphere has 2r, and outer sphere has radius 3r. Plus q1 charge is given to this sphere, plus q2 charge is given to this sphere, and plus q3 charge is given to outer spheres. These are all plus charges. It is given that charge density at outer surface of each sphere is same. That is, let this is sigma. Charge density, surface charge density at outer surface, this surface, at outer surface, this surface, at outer surface, this surface. Outer surface of all spheres have same charge density. So they have asked what is the ratio of Q1, Q2, Q3. That is, charge is given to each sphere. This charge has this sphere external charge Q1, this sphere external charge Q2, this sphere has external charge Q3. So this is very simple problem. We will find it with the help of Gauss's law. Again I am repeating, outer surfaces of all three spheres have same charge density, that is sigma. Now for inner sphere, just use the Gauss's law. Make an imaginary sphere inside the conducting part of this sphere. Electric field will be 0 in this Gaussian surface. So when you will find E dot ds dA through this Gaussian surface, for all parts it will be 0. That is flux. By Gauss's law, this is equal to Q net by epsilon 0. That is Q by epsilon 0. So you can say integral, that is flux through this Gaussian surface is 0, which is inside the metallic part of inner sphere. Flux is 0, hence Q by epsilon 0, that is net charge inside this Gaussian surface is 0. Hence you can say net charge, that is Q is equal to 0. Inside the Gaussian surface, Q is 0. You can say inner surface will have 0 charge. Inner surface of this sphere will have 0 charge by Gauss's law. So you can see this plus Q charge will be distributed at outer surface of inner sphere. Outer surface has plus Q charge and inner surface has 0 charge. We have found with the help of Gauss's law. Now we have also found that facing surfaces of whether it is spherical or it is parallel, they always have equal and opposite charge. By Gauss's law we have discussed it earlier. Outer surface has plus Q charge, plus Q1 charge. So inner surface of this middle sphere will have minus Q1 charge, because these are facing surfaces. Outer surface of inner sphere and inner surface of this middle sphere are facing surfaces. So they have equal and opposite charge. By Gauss's law we have discussed it. So inner surface of middle sphere will have minus Q1 charge. As the total charge on this middle sphere is plus Q2, hence outer surface will have plus Q2 plus Q1 charge. Total charge on this sphere is Q2. Inner surface will have induced charge minus Q1, hence outer surface will have Q2 plus Q1, and total charge is Q2 plus Q1 minus Q1 is equal to Q2. By charge conservation, outer surface of this sphere will have plus Q1 plus Q2 charge. Now again, for these two facing surfaces, this has plus Q1 plus Q2 charge. So induced charge at this surface will be minus Q1 plus Q2. So the inner surface of outer sphere will have minus Q1 plus Q2 induced charge, because these are facing surfaces. this surface and this surface is facing surface. Both these surfaces are facing, they will have equal and opposite charge. Now by charge conservation on this sphere, the outer surface will have Q1 plus Q2 plus Q3 charge, because total charge on this outer sphere is Q3. So Q1 plus Q2 minus Q1 plus minus Q2 plus Q3, that is net charge is Q3 on this outer sphere. So by Gauss's law we have found that inner sphere will have 0 charge at the inner surface, plus Q1 charge at the outer surface, plus Q1 charge will induce minus Q1 charge in this surface, middle sphere. By charge conservation, this surface will have plus Q1 plus Q2 charge, because net charge of this sphere is Q2. This plus Q1 plus Q2 charge on this surface will induce equal and opposite charge at this surface, inner surface of outer sphere, that is minus Q1 plus Q2. By charge conservation, total charge on this sphere is Q3, hence outer surface will have Q1 plus Q2 plus Q3 charge, and net charge is this plus this is equal to Q3. Now it is given that charge density is same. Charge density at outer surfaces is same. So for inner sphere, charge density, surface charge density is Q1 by 4 pi r square. Q1 by 4 pi r square. For middle sphere, outer surface will have charge density Q1 plus Q2 by 4 pi, radius is 2r square. And this sphere will have outer surface charge density Q1 plus Q2 plus Q3 divided by surface area, that is 4 pi, and radius is 3r square. So these surface charge density are same at outer surfaces of sphere. Now you can equate, you can find Q1 is equal to 4 pi sigma r square. Q1 plus Q2, from this equation Q1 plus Q2 is 16 pi sigma r square. From this equation Q1 plus Q2 plus Q3 is equal to 36 pi sigma r square. So this is given. Now from these two equations, this is Q1. So here you can find Q1 is 4 pi sigma r square. So Q2 is, this implies that Q2 is equal to 12 pi sigma r square. Q1 plus Q2 is 16. So Q3 is this minus Q1 plus Q2, that is 16. Q3 is 20 pi sigma r square. So you have found Q1, Q2 and Q3. Now you can find the ratio. So Q1 ratio of Q2 ratio of Q3 is equal to, Q1 is 4 pi sigma r square, 12 pi sigma r square, ratio 20 pi sigma r square. So this ratio is 4 raised to 12 raised to 20. This can be written as 1 raised to 3 raised to 5. Q2 Q3 is equal to 1 raised to 3 raised to 5. So Q1 ratio of Q1, Q2, Q3 is 1, 3, 5. So that is how we have found by Gauss's law charge distribution at inner and outer surfaces of these three concentric spheres, and then we have found ratio of charges which are given individually which are given to every sphere, which results equal surface charge density. So similarly we can use Gauss's law in gravity also, but it is not frequently used in gravity, but because it is applicable for all vector fields, so we will just take a simple example of Gauss's law for gravitational field. So let this is Earth. This is Earth and this is mass of Earth m, and this is radius of Earth. We want to find gravitational field at a small radius r. Inside the Earth, which is located at r distance from center, we want to find gravitational field. So we will find gravitational field by Gauss's theorem in integral form. So just make a Gaussian surface, that is the mass of Earth, this is the radius of Earth, and this is the point P where we want to find gravitational field inside the Earth. So just create a spherical surface of Gaussian surface consisting this point P. So this is a sphere. Now we know at all points, these all points are symmetric on this Gaussian surface because they are at equal distance from center. So they will carry same physical property. Hence, gravitational field at all these points in Gaussian surface will be same, that magnitude, and the direction will be towards center. Direction of G towards center by Newton's law we know. So we will carry out flux, find the flux G dot dA for all points on this sphere Gaussian surface. dA is outward, that is for this surface area vector is always outward from the closed surface. So this is dA, for this part this is dA, for this part this is dA. So we know dA and G both are opposite at every point, so their dot product will be negative, and G dot dA will be minus G into dA, you can say, because both are opposite vector, hence dot product will be negative, and this is magnitude of G and this is magnitude of area vector. So for whole surface G is uniform because all points are symmetric. So G is uniform, minus G you just take, and dA you will add the area of whole sphere, and this is 4 pi r square. So dot product in this Gaussian surface is G dot dA, and this will be carried out for every small element on the Gaussian surface. It will give minus G 4 pi r square, and this will be equal to minus 4 pi G, minus 4 pi G, and M is the mass bounded by this Gaussian surface. So what will be the mass? Mass is nothing but you find density of Earth, that is M by 4 by 3 pi r cube. This is the density of Earth into volume of Gaussian sphere, that is 4 by 3 into pi into small r cube. So this minus minus sign you can cancel. 4 pi you can also cancel. So from this you can say G is equal to 4 by 3 pi also you can cancel, and this r square you can cancel with r cube, only r will remain. So the G is G m small r divided by capital R. Capital R is the radius of Earth, small r is the distance of point inside Earth from center. So gravitational field inside Earth at distance small r from center is given by this equation. So inside the Earth gravitational field you can also plot graph. This is G and this is center from a distance from center. So you see G is the constant, mass is constant and capital R is also constant, radius of Earth. So G will linearly increase up to this point. This point R is radius of Earth and after that G will decrease. So this is analogous to a charged sphere with insulating material, non-conducting material. So same up to radius of Earth, G will be maximum and G will increase linearly, and after that G will have inverse relation, which you know by Newton's law of motion. And similarly, as we have found in non-conducting material, you can find G at distance R dash, where R dash is outside the Earth. So by Gauss's law or by Newton's law, you will find G is equal to Gm by R dash square. So after the surface of Earth, value of gravitational field will decrease with increasing distance from center. So it will decrease like this. So this is how you can apply Gauss's law in gravitational field also. And now we will discuss about Ampere's law. We will discuss about Ampere's law and its application. As we have seen in Gauss's law, we create a Gaussian surface so that finding flux is easy. We create a suitable Gaussian surface. Similarly, in Ampere's law, we create a suitable path so that V dot dl is easy. Line integration is easy. Here we were making surface integration easy. Here we have to choose path suitably so that line integration can be found easily without actually carrying out integration. Only then Ampere's law will simplify the problem. So we will just take simple example of Ampere's law. That this is a current carrying wire. It is having current I. Now it is an infinitely long wire. Find the magnetic field at a distance r. This is point P. So here also we will use method of symmetry, and suitably we will create path, curve, so that this line integration can be found easily. So to find line integration, we will create a circular path, where the wire is at the center of circle and the path is circular carrying this point P. So the radius of circle will be R. So this is the current I. Now we know the magnetic field. These points are located on circle, and these points will have same amount of magnetic field by symmetry, because these points are located at same distance from wire. That is, the point on this circle are located at same distance from wire. Hence these points are symmetric for wire, and they will carry same magnitude of physical property, which is magnetic field. First, that means magnitude of magnetic field by symmetry will be same at all points on this circle. Second, here we see dl. dl is any small displacement vector on this circle, and the direction of dl is towards the tangent at the point. At any point, dl will be towards the direction of tangent. Now we know by right hand rule, the direction of magnetic field due to this wire will also be tangent in the tangential direction. At all points, the direction of magnetic field is tangential. and the magnitude of magnetic field is same at all points. So now to calculate circulation, that is line integration along this closed circle, we know B dot dl. For a small part, we know B and dl are in same direction. So it will be magnitude of B into magnitude of dl, because both are in same direction. Direction of dl, that is displacement vector, is tangential, and direction of magnetic field at all point is also tangential by right hand rule. So B dot dl for a small displacement vector throughout the circular path will be magnitude of B into magnitude of dl for all parts. Now B is constant for all points. We know these are symmetric points, hence B into, so integration of B dot dl circulation will be B into total distance, that is 2 pi r. B is same for all points. When you will carry out B dot dl for different elements, then you can take B common, and dl you can add for all elements. So addition of dl for all elements will give you the circumference, that is 2 pi r. So circulation is B into 2 pi r. By Ampere's law, this is equal to mu 0 into total current passing through this curve, passing through the closed curve, that is I. So B is equal to, at point P, which is located at distance r, but from infinitely long wire carrying I current, is given by mu 0 I divided by 2 pi r. So that is the Ampere's law. Here also you have seen how easily we can find the magnetic field just by the help of symmetry and by suitably choosing the shape of the curve, which we were using in Gaussian surface, suitably choosing a surface, closed surface and symmetric surface. Here we are suitably choosing a closed curve which is symmetric. All points are symmetric. These two approach help us to find dot product easily without actually carrying out integration. Logically you can find the dot product. This line integration as well as surface integration you can logically find without actually carrying out integration with the help of symmetry method and with the help of suitably choosing the surface, Gaussian surface or curve in case of Ampere's law. So here you can see this is the magnetic field. Now take another case. And this is the cross section of wire. This is the wire, and this is the cross section of wire. Wire having radius r, and the current is flowing through this wire. I current is flowing through this wire vertically downward. Now current density J you can write as I by total area, that is current from unit cross section area is I by pi r square. Now it is asked to find the magnetic field inside the wire at a point having distance small r from center of wire. At point P you have to find magnetic field. To find magnetic field we have created an imaginary curve, circular curve having a small radius r, and this curve will carry point P. Let magnetic field at point P is B. As this curve is circular and all points are symmetric, so we can say magnitude of magnetic field will be same at all points. And direction of dl vector will be tangential as we have discussed earlier for all points, and direction of magnetic field will also be tangential and in same direction because by right hand law. So you can say for all point in this imaginary curve, B dot dl is equal to magnitude of B into magnitude of dl, where B magnitude is constant throughout this circular path by symmetry. So line integration B dot dl for all parts will be equal to B, you can take common because B is same, into total length dl. So total line integration B dot dl is into 2 pi small r, and this is equal to current enclosed by this imaginary circle, that is mu 0 into current density J into, that is a current density, that is current from unit cross section area, and the area of this circle is pi r square. So this in Ampere's law we have discussed, I is total current inside the imaginary curve. So this is imaginary curve and the area of curve is pi into small r square, and J is the current density, that is current from unit cross sectional area. So from pi r square area, current will be J into pi r square. So here you can say this can be written as mu 0. What is J? J is total current I divided by pi capital R square into pi small r square. Pi से pi you can cancel, and B into 2 pi r. So here you can write B is equal to, inside the wire, mu 0 into I divided by r square. This 2 pi you can write here, this r you can cancel this square, so here you can write r. So this is the magnetic field inside the wire carrying its current. If we assume the current is uniformly distributed across the cross section of wire, mu 0 I small r 2 pi capital R square. So here if you draw the graph, just like we have earlier drawn the graph, so this is distance from center of wire, this is magnetic field, and this is distance from center of wire. So you can see the magnetic field is linearly increasing with small r. All other things are constant. Mu 0, I is the total current, pi, and capital R is the radius of wire, that is also constant. So with small r, that is distance from center, this magnetic field is radially increasing. It will increase radially up to this point where small r is equal to capital R, the surface of wire. And after that you can see this will decrease. As we have earlier found the equation of wire, outside this wire, magnetic field is given by B is equal to mu 0 I divided by 2 pi r, where r is the distance, r dash is the distance of wire point from center. So this is inversely proportional to distance from center outside the wire. Magnetic field is inversely proportional. So it is decreased after the surface of wire has reached and you are moving beyond the surface. So this is magnetic field and this is distance from wire. This is how the profile of magnetic field changes inside the wire and outside the wire.